automation and programmability. The high points, I guess, here are automation, network management, device management, controller-based networking, and software-defined networking. That's where users or big companies want to go. When we talk about automation, what we're going to talk about here today, DNA center, software-defined networking, controller maybe, but all of that stuff costs money. The small, probably even to medium-sized enterprise, the big companies are going to buy the automation. This is not a cheap hardware. This is not a cheap thing to do, because a lot of the existing hardware probably will have to be replaced to have compatibility with the controller that we also have to buy, and that's what we're saying is not cheap. These things, the process, the hardware, the management, the doing this is something that's not going to be inexpensive. And when we look at the DNA center, the read-only, you'll see that, we're talking about worldwide management for these things. So big companies, lots of places, dentist office ain't going to do it. Probably even a place like the LeaderQuest campuses. I'm sure that ECPI isn't doing it that way because there's just not that many devices that have to be managed from one location to the other. Automation, network management, device management is going to be our first topic here. Automation, the need for reducing human interaction. And that is the purpose of this, to have fewer techs but better trained techs. I won't say smarter, because better trained, wider range of experience that they would have to do these things. What we're going to do is we want to automate the routine. And again, we'll go back to, and I'll continue to refer back to the wireless LAN controller. If we had those autonomous systems, all of those autonomous systems, we didn't have that many. Let's say we have 30 or 40 systems, and we want to add an SSID and a VLAN to it. We could go into those 30 or 40 systems and do that. Or we could go to the wireless LAN controller and do the configuration, set up the interface, associate it with a VLAN, and then associate an SSID with that VLAN. And it goes, bingo, it goes immediately to those 30 or 40 lightweight access points. And that's what automation is, except that when we're talking about automation now, we're talking about doing that on a larger scale. Network automation, reducing the need for human interaction to configure, manage, deploy, test, monitor physical and virtual network components. Boy, that's a mess. What that says is we want to replace as many people as possible with automation, and that's going on a regular basis in industry. Robotics is doing that. So this is not a foreign concept to what's going on in the world of networking, in the world of production, and a lot of the world. Thousands of tasks in today's computing environment. Lots of tasks are performed automatically on a regular basis. Automation is going to be the key ingredient. Cloud-based solutions is what we're looking at, and there's lots of those that go on, and these can be part of the DevOps initiative. The devnet.cisco.com has got a lot of information that can be used with this thing when we look at these. So controller-based networking, we've done that. We've looked at that in the 2010s and for a long while in the 2010s. We introduced software-defined, which was the first step towards where we're going today, the systems are going today. The controller created the new capabilities, and it makes use of a controller to centralize some of the network functions. Not all of them, but some of the network functions. And we did that with a wireless LAN controller. We centralized some of the functions, management functions, basically, we centralized. But the connection and the checking to be sure they got the right password, all that happened at the hardware. Some things are still going to happen at the hardware. The data shipping is going to happen at the hardware. And that's going to be called the forwarding plane when we get to that. Automatic configuration and operation through application programming interfaces. Sound familiar? Traditional, we go to one device at a time, and that's what we've been doing, and that's what this CCNA is really about. And then it introduces, and this is the first step into controller based. If you move on to CCNP, it gets a little bit more, a bigger portion of it, more functional, I guess, at that point. The CCNA just kind of know about the automation. Enable the automatic configuration of these things. Traditionals, we did that. Software-defined access, again, a new term for software-defined networking. Uses a software-defined architecture. Still uses the networks with switches, routers, and cables. We still have to have the physical devices. They still have to be connected together. It's the way the network is seen and managed is what we're talking about. And I'm going to say probably multiple times, when we do this software-defined access, software-defined architecture, the controller, the things like the Cisco DNA Center knows everything about the network. Therefore, it can do a lot of the management tasks for us. So instead of connecting to each individual resource, we're going to connect to the controller like it's shown here. We got the script, the GUI, the Cisco or vendor, then application, the GUI, whatever we're using to connect to the controller. The controller then, and we have this SBI down here, it's going to be a southbound interface. SBI here, southbound interface, the controller connects to the devices to send the information from the management from one to the other. At the center is the Digital Network Architecture Controller, the DNA Center or DNA Controller, the Digital Network Architecture. And this is a Cisco sort of, I guess, concept. It's more than a concept. It's an actual management process procedure. And again, we'll look at, I got to look it up here in a few minutes. We'll look at a read-only copy of the DNA Center. What does it do? Is a controller for software-defined access. SBI, the southbound interface, contains the fabric, underlay, and overlay. Underlay is the physical connections, and the overlay is the logical, I guess, path would be a good way to say that. Logical path, the best path that this DNA Center determines. DNA Center, again, has absolute knowledge about the network. So it can look in there and say, hey, I've got a problem here, I've got a problem there. And we'll go back to maybe traffic on the interstate. When you get ready to go to work, you got the traffic helo up running around in cities and telling you where there are backups, where there are not backups, where there are delays. Basically, they just report delays, but gives you an idea of what's going on in the traffic flow. That's what happens with the DNA Center, except it's going to have all the reporting coming to it of delays, of addresses, of MAC addresses, IP addresses, all of the other eventualities, the speeds from one to the other. It can go in and find the OSPF, find the shortest path. Terms, and we kind of had those a little bit earlier. The overlay creates a VX LAN tunnels, a new term here. VX LAN tunnels is just the protocol that we use to find the best path through the underlay, which are the physical devices for these things. So the overlay creates VX LAN tunnels between software-defined SDA switches, then used to transport the traffic from one fabric endpoint to another fabric endpoint. And fabric down at the bottom, what is a fabric? It's a combination of overlay and underlay. Provide all of the features to deliver the data access across the network, desired features and attributes. And then the underlay are the physical devices, the connections, the cables, the wireless, the switches, the routers, IP connectivity, all of those things to all of the nodes in the fabric. So the fabric is a combination of those. It's the network itself. The process to create an overlay through the VX LAN tunnels. And when we talk about the VX LAN tunnels, what these things have are, we're going to have endpoints. They're going to register things, and a couple of steps to look at what actually takes place in this process. But we have switch 1 and switch 2 here, switch 1 here, and switch 2 here, and then we say that we have a VXLAN, and we always draw these really cool little neat tunnels, right? What we would have to create our really neat tunnel is a best path, whatever it might be, through the network, and that's where the VXLAN tunnel is going to be, from one to the other, the path that it's going to take. We're going to have a registration protocol that will know where these guys are, and we have switch 1, switch 2. We may have other switches connected to this that have other networks. So we need to find the best path to get to those networks. So the underlay, multi-layer switches, and links with IP connectivity. IP connectivity here is a big deal, and all these show as layer 3 switches. We're not worried about, we're not using layer 2 anymore. Layer 2, we get into the block ports with spanning tree protocol. We don't have any block ports with layer 3. New concepts, the tunneling method is called VXLAN, which is a new protocol that we're using here. I say new, it's new to us, but it's been around for a while. Traffic sent by the endpoints flow through the VXLAN tunnels in the overlay. The physical, the overlay, the VXLAN, the logical flow, spell that right, the different process than the traditional switching or routing. Traditional switching or routing, the calculation is done on the device, and in this case we're going to have some registration, some other thing that goes on in order to create the best path. These techniques, these technologies are one of the reasons that our internet speeds have really increased dramatically. You can go back to just a few years ago, and I think probably 50 meg. Actually, when I first got mine several years ago, we're probably talking over 20. We're all talking over 20, probably 25. It was was 10 meg. That was really fast. Then we went to 50. Then we went to 100, and now the general standard speed for cable modem, I think, is around 200 meg. At least that's what it is here, and that's what it was in Charlotte. So we're going faster and faster and faster. What happened? We got more infrastructure, but we got better technologies in getting the information, the data from point A to point B. Better utilization of what goes on. A lot of new hardware, obviously, when we do that can use those technologies. And the migrating, what this basically says is, if you're migrating from one to the other, don't do it. Buy new hardware. Possibility of harming the existing production configuration of the DNA center should not be used to configure the underlay if the devices are currently used in production. So what it's saying is that we need to start over with the devices that support and devices that are not being used in the network today, in the technologies that we're using. Existing hardware got to be from the SDA compatibility list. Hey, maybe got to buy a bunch of new hardware. And again, goes back to, this is not an inexpensive proposal or process to do these things. So is everybody going to do it? Yeah, maybe not. The intermediate side probably not going to go to the expense of replacing all of the equipment, buying the controllers to do these things. Wireless, maybe, because how many wireless access points you're going to have? If you have 3 or 4, are you going to buy a wireless LAN controller? Probably not. And when I say those are my opinion. That's not anything that's based in fact. The device software levels must meet the requirements based on the roles as detailed in the compatibility list. And the roles that we're going to have with these things, we're going to have an image here in a little bit that hopefully will show these things. We're going to have the fabric edge node that connects the endpoints, similar to the traditional access switches. The fabric border node that connects to the devices outside the SDA's control switches that connect to the WAN routers, in the data center, and then the fabric control node, and this is the one that's going to use the underlay for LISP, which is a locating protocol. New term, new protocol. Each of these more CPU, more memory, and probably different features of the iOS. The new SDA architecture that we have can be added into the campus LAN, but there's going to be risks. If we use new gear, it's going to remove the challenges. The LAN design points have to be there. The number of ports, I mean, what are we going to need? How many ports are we going to need? The number of ports on the switches in each wiring closet. Port speeds, benefit of a switch stack in each wiring closet. And switch stack is a new term. What a switch stack does is takes multiple switches and stack them actually, and connect them together and treat all of these switches as a single unit. Manage all of them. We're going to have a master, and we'll configure the master, and then the master will send the configurations to all of the other devices. Another, kind of automating, fewer devices to manage, put them together. So what the network will see is, instead of a 24-port switch, maybe see a 400 or 500 port switch that is on the network. So we need to know the number of ports, switch stack in the wiring closets, cable lengths, type of cable, power over Ethernet, power available in each new switch versus the requirements. And this is one, is it enough? The power. There are two, and I don't remember the numbers, two power over Ethernet standards. One of them has a higher power than the other. Voltages are going to be the same, but the amperage requirements are going to be what we have. And remember that breakers, the standard breaker size is going to be 15 amps. So we may need something bigger than that for our switch. The link capacity, the speed, and the number of links between the switches. How are we going to connect all this together? And this is what we're talking about. This is the new SDA architecture. We're talking about the planning that needs to go in before we put in this new SDA architecture, software defined access. The traditional, we're going to do the traditional and the SDA. The traditional here, we're going to have this shows a layer 2 switch, which means we're going to have spanning tree for these things. The layer 3 switches can act as the default gateway used by the hosts. Often implemented HSRP, the hot standby routing protocol, which we did. Better availability, one of them is waiting for another one to fail so that it can take over. If we do have a failure, one will immediately take over. More than one uplink from the access or distribution layer switches. The access layer switch here, we've got a layer 2 switch. The distribution layer, we have layer 3 switches, but the layer 2 is obviously going to go to a layer 2 topology, layer 2 to layer 2. And over here on the right here, we show a block. So we're going to have a block here. We're going to have spanning tree protocol to do these things. So this is going to be our path. Something happens here, then this will be unblocked and we can use the path. HSRP, one goes down, the other one can take over for the protocol, for the routing functionality for these things. And the number of configurations have to take place for the HSRP to work correctly. And these circles here means that we have ether channel here for these things, or lag aggregation, link aggregation, LAG, lag. An ether channel is the link aggregation that we're going to use. So this says that the most design uses more than one uplink for these things, from the access to the distribution layer. From the access down here where we access the network using layer 2 switches. With the layer 2 ether channels allow balancing in addition to redundancy, and we do the balancing with the root switch, root per VLAN, and we can make each VLAN have a different root switch, and so that we can have this as blocked. It may be blocked for VLAN 12 but open for VLAN 40, and this one would be blocked for VLAN 40 and open for VLAN 12 when we do these things. STP, Rapid Spanning Tree, manages the layer 2 redundancy in the campus, prevents loops by blocking the ports. So we're not going to have the full capability available to us. How do we do that? Remember, the only way to block layer 2, since we didn't have the hop count in there, is to actually block a port. Layer 3, when we use the layer 3 access, and the only thing that we're using layer 3 connectivity, but what we've done is to add a layer 3 switch here, so that now we don't have a block port. We don't have to have HSRP. We don't have to have Rapid Spanning Tree Protocol, per VLAN Rapid Spanning Tree Protocol. All of these things are open when we do these things. The Greenfield SDA fabric uses routed access layer design. Routed access layer have been around for a long time before SDA, but makes use of the design, and it works well for the underlay, the underlay, the physical, to support the VXLAN tunnels in the overlay, the virtual, or the logical. Routed access layer means that all the LAN switches are layer 3 switches with routing enabled, and we do have to enable routing, and it's just the way you do that, you go into config on one of these things, and IP routing, and that will turn on routing, IPv4, IPv6 unicast routing if we want to turn on IPv6 routing. All the links operate at layer 3, which means that we're going to have no block ports, no block ports. We're going to have access because we have the hop count, the TTL. Now, TTL, time to live, is hop count when we do these things. How many devices can we go across, and basically how many times is it going to go around before, if we get into a loop, before it gives us an error message back. The routed access layer, all the switches are layer 3 switches, and in this case, they say in the book that I use for this says it's going to use the IS to IS routing protocol. I don't know that you necessarily have to use that. That's the one that the official Cisco guide said would be used for this. All links, single links, all links between the switches are routed layer 3 links, not layer 2 links. So spanning tree is not a factor. Spanning tree, rapid spanning tree, whichever one we're using, is not going to be necessary, and we would really want to use the rapid because of the more rapid reconfiguration of the network. The routing protocol, instead of choosing which links to use based on the IP routing tables, equivalent of a traditional access layer switch, the SDA edge node acts as the default gateway for the endpoints rather than the distribution switch. HSRP, or any first hop redundancy protocol, isn't needed anymore. So when we look at this thing, this HSRP, hot standby routing protocol, or VRRP, whichever we're using, virtual address would be the default gateway. We would have the block ports. We have a limited connectivity because of the layer 2 protocols that we're using. When we go to the layer 3 SDA fabric and use a layer 3 switch, this is now down here, the access layer switch is now the default gateway. And it can get into the routing technologies, topologies, protocols that it needs to find the paths that we need to go from one to the other. So the overlay that we have here, the SDA overlay sequence, the endpoint sends a frame. The first SDA node encapsulates a new message with the VXLAN tunnel, and it forwards it into the fabric. It's encapsulated the remaining nodes forward based upon the VXLAN details. And the VXLAN details are going to be a situation that it finds the best path across the network for the destination that this guy is going to have. We have IP here, our IP network, our TCP, our transport layer, and then in here we're going to have the VXLAN, and then we have the LAN frame, the framing that goes on. So Once we get into the tunneling, the VXLAN encapsulation, the VXLAN protocol is going to be used to send it from location to location. So, and just like everything else, we go into the tunnel, the ingress fabric edge node, go through the tunnel, and then we have the egress node where it removes the encapsulation. So it removes the VXLAN, and we have a standard IP packet that can now be processed by all of the other routers that might be in here and the device itself to get from one to the other. So the LAN frame, the local area network frame, goes into this thing, and we're going to go through the network using a different topology, another topology, a new topology, or whatever we're going to say. The VXLAN tunneling, encapsulation and de-encapsulation, performed by the ASICs, the application-specific integrated circuits, and that's what switches used to do the switching. So now we're going from software to hardware, so that's automatically going to make it faster. The ASICs is going to perform things faster, so there's no performance penalty for these things. One reason the SDA hardware compatibility list, the switches have to have the ASICs that can perform the work. So the hardware compatibility list that we saw a little earlier, why do we need that? So that it can actually do its job to get from. The VXLAN encapsulation supplies the header fields the SDA needs for its features so that the tunneling protocol is flexible, extensible, while being supported by the switch ASICs, the application-specific integrated circuits that we would have. Tunneling needs to encapsulate the entire data link, and then to support encapsulation, the underlay uses a separate IP address space, and that's what both of these are. This one doesn't have the ingress and the egress in it, but that's what this one's supposed to show over here. Unfortunately, we use 10 for both of these, but we have 10.1.1.1, 10.1.2.2 over here, and then the tunnel itself is using a 10.3.3. Going from one to the other, each of them is going to use the different IP addressing schemes to go from one location to the other. And then we're going to have another protocol, the LISP, which is the location, ID, and separation protocol. And if you go do a search on YouTube, you're not going to get this one. You have to do LISP network protocol to do this. Location, ID, separation protocol. Consider how the traditional devices discover the addresses that we do these things. And we have different ways to discover the addresses. We have the protocols discover the addresses. We have the MAC address table discover the addresses. What's going to happen here is they're going to register. Switches examine the source MAC address for these things, software-defined access. The fabric edge nodes learn of the possible endpoints, what's attached to them. And once that happens, it registers the fact that it can reach these particular devices, this network, this 192.168.1 network, this 10.17.14.0 network for these things. So they get registered with the fabric edge nodes. And then it registers the fact, and then it registers into a database called the LISP map server. And the LISP map server is then it keeps a list of the endpoint identifiers and match them with the routing locators. The future message is for the lookup, find the destination in the LISP database. It's going to tell us what the best path is to get from one to the other. So the LISP format here, the header information, the version, we have the IP outer header, router supplies the RLOCs, the router locators, UDP, the LISP header, and then the IP inner header supplies the end devices, the end device IDs for these things. So a number of things go on with this. So where do all of these things locate? We have the interior network here. We got the LISP site A EID. So okay, the LISP, we register the 8.8, the 16s here, and the IPv6s. And the RLOC, the routing locators here, send the information from end to end, and then they go back to the LISP. We're also going to have the ability here to automatically, I guess, calculate the best path to get from one to the other. A couple of maybe help a little bit, maybe not. Edge nodes register IPv4 prefixes. The endpoint IDs, the EIDs with these things, with the LISP map server. So the endpoint ID here, 10.1.3.0/24. The RLOC, the routing locator that it registers with, this routing locator knows how to get to me. The other one here, let's see if I can get these straight down here. RLOC 172.16.4.4, the other EID, a 10.1.4. And these routing locators send that information to the LISP, the location ID, the location system network, that's the map server that's going to keep a complete mapping of what goes on. So at the ingress tunnel, the destination 10.1.3.1, which is over here on this one, is going to go to its switch. Its switch then goes to the LISP map server. So we have the one here, the two, that we get what the one and the two would be getting into this location. And then we go 3 to the switch to the LISP map server. 4, 5 looks at the database. 6, the RLOC here, and then we're going to connect the two switches together with the VXLAN in order to send the information from one location. Again, new technology, different technology that allows us faster, more expensive, the destination. And here we use a different IP. This is the destination network, the original, and then the VXLAN, the IP address of the next hop here, the RLOC, the routing locator device that we use for this thing. And when it gets here, all of this gets stripped off, and we have the original packet, which goes back here to the destination IP address with it. The next is kind of a step by step what goes on. Step 1, the initiating host resolves the DNS name to the endpoint ID. Next, it sends the packet to the SEID, EID 10.0.0.1 here, and then the ITR receives the packet, and then the mapping is performed to find the outgress, the egress RLOC when we do these things, and then after realizing the remote RLOC encapsulates the EID packet with the tunnel header and sends it into to the router. And then at the end, the ETR, the egress terminal router, the ingress terminal router, egress input and output for these things. And then the underlay are all of the devices that are in here. The overlay is the virtual path that it's going to take to get from point A. So the summary slide, I'm going to leave the summary slide here. I have a knack of taking a break just before we're about the end of a section, but that's okay. So the overlay and the underlay networks, we've talked about that. And what are they? The overlay is the virtual network, the underlay, the physical devices. Most SDN, the software-defined networking, and the terminology, software-defined networking, software-defined access, related to each other, are carried out on existing networks. The SDNs are. Existing switches and routers can remain in place with it, and the technologies linked to the physical device is going to improve the flexibility. What we're doing here is showing here in the image is that we're taking the traditional networking where we go to one at a time. We have the switch, the device, the switch or the router, whatever we're using, and we have the control plane and the data plane. And we'll look at some slides a little later on, but the control plane is the thing that controls or management. It's the intelligence, I guess would be a word that we would use, of the device itself. The routing protocols, finding the MAC addresses would be there. So what we're doing is taking those functions off of the devices, taking the quote intelligence unquote off of the devices, putting them in a centralized controller machine, and then sending the information to the what are now worker bees, the data plane, the data shipping plane, it will now do the work based on what it's told from the controller machine. Not really a new concept, but how do we do that? What are the things that we need in order to do that? Overlay and underlay. The underlay network, the physical structure of it. The overlay network, the virtual switches here. The virtual, just like we have virtual machines, we have to have underlying the virtual machine. We have to have a physical machine underlying the virtual network, the overlay network. We have to have a network that actually is able to take the data on an interface from a piece of media and put it out another interface on a piece of media and get it to the next device. Traditional manage and update, each one separately, does not scale well to large networks. Prone to errors. Or do we make a typo? Have we been able to consistently make the changes on the 47 devices that we had to update today, and then another 50 tomorrow? The objective again for automation is to be able to do the repetitive tasks on this multitude of devices from a central location. The Cisco DNA Center, we have the REST APIs for these things. We show that we have GUI script, whatever we're going to use in order to get into it, and then the southbound interface this is going to be the northbound interface is what we connect to. The southbound interface is going to be what everybody else connects to, or where the controller connects to the physical devices. This is what is the Cisco DNA Architecture Center, centralized management platform, controller management and analytics capabilities, and then it's an open extensible platform to allow the configurations of these changes.